Welcome. In this session in linear data analysis, we'll explore principal components analysis, or PCA, using the Rayleigh quotient. Let's recall where we are from a previous session. We were looking for the principal axis from PCA. Here I'm going to use a temporary variable t, and what we said was that the principal axis, which we'll call the vector w, is the result of finding the maximum input or argument to this. This is the quadratic form using the scatter matrix. So we want the main axis of PCA to be the result of this quadratic form, and we want to maximize it. And in the previous session we had this extra constraint, which is that we want this to be a unit vector. That is, we want W to be a unit vector, and so that means that we have to do a search over all unit vectors of these quadratic forms. Now, it's not immediately apparent how to do that. So let's relax this a little bit and let's make a substitution. Let's suppose that this vector t, this temporary vector, is, let's say it's any non-zero vector u that's in the vector space, that is, that it has n entries, where n is the number of variables in our problem, and we'll take u and we'll just divide u by the ordinary vector norm of u. And if we do that, what we do is we transform this from what's called a constrained optimization problem into a general optimization problem. So now our problem is this. We want to find a W that is the argument maximum. Now it's over all u vectors that have n entries, and we'll have this side condition, which we almost always have in linear algebra, which is that u can't be zero. And it's now we can represent this as, so I'll take t, so I'll put u transpose s u, and now I have to divide by the square of the norm of u. And one way that I can divide by the square of the norm of u is I can divide by u transpose u, because u transpose u is the squared ordinary norm. And so I could say that that is u transpose u. This term is familiar to us if we read some mathematical history, because this is attributable to Lord Rayleigh. Lord Rayleigh is a Nobel laureate. He was a physicist, he was a mathematician, and the Rayleigh quotient is definable in this way. So let's put an underscore, because that's going to appear in subsequent sessions. The Rayleigh quotient, we'll define this as a Rayleigh quotient, and it takes a matrix and it takes a vector. And so this will equal by definition. And let's just computationally handle that zero case, because we're computer scientists and we like to be sure that we can perform a computation. So that will be this term, which is u transpose su over u transpose u, if u is not the zero vector, and otherwise we'll say that this just returns zero, because zero is the limiting case of this. So it will return zero if u equals the zero vector. So I can now use the Rayleigh quotient and reformulate this problem. So now let's do that, and let's just, before we do that, let's recall some terms. Let's recall that we said that lambda max of a matrix, and here I'll just put a matrix B, because our matrices that we're going to work with are always symmetric, positive, definite. So that is the largest eigenvalue, and V max of a matrix is the associated eigenvector. And so these are what we can use. And this is a fact. So let's remember, for us, the fact is something that is true that we're not going to prove in these sessions. And this is proved in the extra notes for this course. And that is that if we take the ordinary maximum over all u vectors that have n entries of the Rayleigh quotient of any matrix and a u vector, that equals lambda max of that matrix. That is, the maximum value of the Rayleigh quotient is the largest eigenvalue of this symmetric matrix. And if we look at the problem that we have now, which is an argmax of u having n entries of the Rayleigh quotient of this matrix, then that is the associated eigenvector of that matrix. And so what we now have is yet another way that we can think of principal components analysis, or PCA. Previously, we've thought it as related to the covariance matrix. Then we found that it was related to eigenvalues and eigenvectors of the scatter matrix. Now that continues to be true, but we can also say that the principal axis is the result of finding the maximum input argument for the Rayleigh quotient, and we can say that the first latent variable is the result of a maximum of the Rayleigh quotient itself. So we can now use the Rayleigh quotient and formulate those terms that we previously had, that we were previously using the covariance matrix for, and then just a little bit we were using the scatter matrix for. Let's briefly summarize what we understand now about principal components analysis. The principal loading vector that we find in PCA is the main way that we describe a covariance matrix. We're discovering that it's providing scores of how the data vary from the mean, and we find that it's a solution to an optimization problem. In addition, we can describe this using the Rayleigh quotient of the scatter matrix rather than using the covariance matrix. So, what have we learned in this lecture? Well, we're now able to relate these PCA scores to singular vectors. We can interpret PCA as a maximization process, and we can describe the principal PCA axis as the solution to a problem that involves the Rayleigh quotient.